Hello everyone, I am Saaketh Desai. I am a graduate student in the School of Materials Engineering at Purdue University, and today I will tell you about neural networks and their applications in material science and engineering. This is a part of a series on data science for material science and engineering, and this module consists of three parts: an introduction to the basic concepts of neural networks that will be covered in this lecture, a hands-on tutorial that will look at the programming aspects of creating your own neural networks for regression and classification, and a homework assignment that will test both the fundamental concepts covered in this lecture and the programming aspects covered in the hands-on tutorial. So without any further ado, let's just jump right into it. The learning objective for this module and this lecture will be for you to be able to create and train your own neural network for either a regression or a classification task. We will also look at how to avoid some common pitfalls such as overfitting or underfitting your neural network, and see methods that will allow us to train an optimal model given our dataset. The prerequisites for this model and this lecture is a familiarity with basic Python programming, since a lot of the code in the hands-on tutorials is in Python. Some familiarity with querying materials repositories for data is also useful, since the data that we will obtain to train these neural networks will be from various materials repositories, so some understanding of how to perform such queries is also useful. Lastly, one prerequisite that will be useful is the structure of the code used to fit a linear model to our data. This was covered in the linear regression tutorial. A lot of the code structure will remain the same. Today, we will swap out the linear model for a neural network. And if you want to catch up on any of these prerequisites or revisit some of those concepts, I would encourage you to look at some of the resources on NanoHub or look at some of the previous modules in this series. Before I begin talking about neural networks, I wanted to give a big picture overview of data science and machine learning in science and engineering, and give today's lecture some context. The broad theme of this series is to explore data science and machine learning methods in material science, the big concept of which is learning from data. And there are various aspects to this, some of which we have already covered in this series, some of which we will continue to. For instance, the first module talked about acquiring and handling data. A wide variety of data sets are existing today in materials project, Citrination. We've looked at how to acquire and handle such data sets. And some previous modules also talked about developing predictive models. We started with linear regression, but the goal is to develop predictive models given the data that we have queried. This is often called supervised learning, and today we will explore one facet of this, neural networks. Subsequent modules will talk about finding patterns in your datasets, often called unsupervised learning, where the goal is to often reduce a high dimensional problem into a low dimensional space and find patterns in your data that best describe it. And subsequent modules will also cover design of experiments, where we use machine learning methods to inform the next experiment that should be conducted to achieve an optimal material faster than possible with brute force or with scientific intuition. All of these data science and machine learning concepts can be realized in practice only with cyber infrastructure. The cyber infrastructure of our choice is NanoHub, which is already connected to a wide variety of materials datasets like Citrine Informatics, Materials Project, Wolfram Alpha, and additionally also consists of various machine learning libraries and packages pre-installed for you. Today, we will look at neural networks, a form of supervised learning where we will develop predictive models for our datasets using a neural network. And to look at these neural networks as predictive models, we can step back and abstract our understanding of a model in this picture here. This picture is helpful as we will understand how various models compare and contrast to each other, and we will see how a neural network gives us some of the benefits that are widely known. Our general view of a model is going to be a box that connects inputs to outputs. The inputs in this case are x1, x2, and x3, and the output is y. And there are various different models that you can use. The previous module talked about linear regression, where you fit a linear model to the dataset. So for instance, y is ax1 plus bx2 plus cx3. A, B, and C are the coefficients of our linear model in this case. An example of this could be predicting the cost of a house given the area. We would imagine that the bigger the house, the more expensive it would be. So the cost of the house could be linearly related to the area of the house, for example. And if so, we can fit a straight line to our data and compute the coefficients that best describe our data. Sometimes a linear model is not good enough to describe the data, in which case we might opt for higher order models. Shown here is a quadratic model, which has a second order term in the variable x1, which means that y varies quadratically as x1 varies. And today we will look at neural networks, which are just another extension of some of these models, except they offer some unique capabilities. So for us right now, a neural networks is literally a black box which connects the output y to the inputs x1, x2, x3, which we can write in this way. But before we dig into the inner workings of this black box, some useful features of this neural network that make it stand out from some of these simpler models like the linear model and the quadratic model are that these neural networks are proven to be universal approximators. And by that, I mean that certain structures of this neural network are proven to learn any functional mapping between the output y and the inputs x1, x2, and x3, which is very useful because we know that fundamentally it is possible for a neural network to learn every single mapping. Additionally, these neural networks learn by example, and by that I mean that to train a neural network, you have to show it many different input-output pairs, so input 1, input 2, output 2, and so on and so forth, till the neural network figures out the underlying mapping that connects the outputs to the inputs. And these features of a neural network make it very desirable compared to some of the previous models that we have seen before. And in today's lecture, we will see the inner workings of a neural network and how some of these features that I've covered here come into practice when training your own neural networks. Before I dive deep into that though, we know various applications of neural networks in science and engineering, and I just wanted to give you some examples of how these neural networks are being used, not just in self-driving cars or in social media recommendation engines, but in examples closer to the kind of work that you will encounter as scientists or engineers. The first example that I wanted to talk about was the use of neural networks to predict protein structures. Now, predicting the structure of a protein is traditionally been an extremely challenging task involving significant experiments and computations. These neural networks, on the other hand, have shown great promise in looking at a wide data set of protein structures and figuring out the underlying mappings that best describe a protein structure, reducing the time required to solve this problem drastically. And one neat example of this is the use of these very neural networks to predict the structures of the proteins involved in the COVID-19 virus. So shown here, in fact, is a prediction of one of the proteins involved in that virus. Something closer to the materials world is the use of neural networks to predict the stability of compounds. A neural network has again shown promise here in just looking at some elemental information like electronegativities, atomic radii, and the composition of the various elements, and predicting whether the compound is stable or not. And while these examples that I talked about were research grade and involved training extensive neural networks with state-of-the-art datasets, today I wanted to get you started with a very simple example in the hope that this simple example and the concepts that you learn here will be useful and carry forward as you move on to your application of interest. The simple application that I wanted to talk about was predicting the Young's modulus of a material given some atomic information. Now, the Young's modulus of a material is a property that fundamentally arises from the interactions between the atoms, which are often represented in this sort of a curve here, which is the potential energy of the interaction between two atoms as a function of the separation between the two atoms. So if the atoms are very far apart, they barely see each other, and as the atoms come closer together, they form a bond, and the strength of this bond decides properties such as the melting temperature, while the stiffness of this curve gives us the Young's modulus. And in the previous module, we tried using this insight to just develop a linear model. And we saw that a linear model doesn't quite fully capture the correlations. So the question that we ask is, can we predict the Young's modulus of various elements given periodic table properties such as heat of formations, lattice constants, atomic mass, atomic radius, etc.? Kind of similar to the example that I just talked about, where the neural network predicted the stability of the compound given such elemental information. In this example, we are predicting the Young's modulus only for single elements, so the problem is much simpler. But how do we go about doing this? I think it's time to crack open the black box and see what we have inside. The structure of our neural network is going to be largely inspired from the structure of the network of real neurons in your brain, which are simplified to look kind of like this. So this is a neuron which has dendrites that collect electrical signals as inputs, passes it along to an axon where the electrical signals are then passed on to the next neuron. And we will abstract this process in our neural network by schematically showing our neural network to take in some inputs, make some computations, and predict an output. That is, in this case, the Young's modulus. So when we take a look inside this black box, what we find is a structure like this. So we have an input layer, which is the melting temperature and the resistivity, the two inputs in this schematic. The output layer, which is the Young's modulus predicted by the network, and a hidden layer, which consists, in this case, of two neurons, A1 and A2. Now, a general neural network, like the ones you will train in the hands-on session or the ones that you saw in the research-grade examples, will have many hidden layers with many different neurons. But for this example, we will stick with one hidden layer that has two neurons, A1 and A2. So for us to compute the value of the Young's modulus, given this neural network model, we need to perform what is called a forward propagation. So given two inputs, melting temperature and resistivity, we need to propagate forward through this network to compute the Young's modulus. And the way to do that is using this equation, which might look like a lot at first, but it's fundamentally very simple. To compute the Young's modulus, we first need to compute the values of neurons A1 and A2. And to compute the value of each neuron, we will look at all the inputs to that neuron, linearly combine all those inputs with weights and biases, and apply nonlinear activation functions to that combination to get the value of our neuron. So what does this mean in practice? Let's try working out the value of neuron A1. We said that we would look at all the inputs to the neuron, which is the melting temperature and the resistivity, linearly combine them with weights and biases. So let's call the weights W1 and W2. So we can linearly combine our two inputs by saying W1 times melting temperature plus W2 times resistivity plus a bias term B1 is the input to A1. And we said we will apply a nonlinear activation to that combination. That activation is described by the function f1 here. We will look at what this is in a second, but this is a nonlinear function that will transform this input into the value for our neuron A1. So let's look at another example so that this process is solidified in our head. To compute the value for neuron A2, we will look at the inputs to that neuron, which is the melting temperature and the resistivity. Again, linearly combine them. These weights are now W3 and W4, a bias term P2, and we apply a nonlinear activation to this combination, and we're calling this activation F2. Having computed the values A1 and A2, we can repeat the same process to compute the Young's modulus, that is the prediction of our model. Again, the inputs to this model are A1 and A2. We linearly combine them, so W5 times A1 plus W6 times A2 plus a bias term B3, and apply a nonlinear activation, which I'm calling F3 here. And that's it. We have predicted the Young's modulus given the inputs melting temperature and resistivity for this very simple neural network. So how do we go about using this in practice? Well, before we understand that, we need to look at the activation functions. Now, the simplest activation function is a linear function, which takes in the input x and returns the same value. So which means that it would take in this combination here of weights and biases, and return exactly the same number, which is not very useful in most cases, but sometimes it is very useful, especially in predicting the outputs, for instance. Some other activation functions are the hyperbolic tangent, which restricts the output to be between -1 and 1. Another popular activation function is the rectified linear unit, also called ReLU, which returns the input as it is if the input is positive, or returns 0 if the input is negative. So these are some common activation functions that are used in training neural networks, and we will use some of this in the hands-on tutorial to predict the Young's modulus, and a little bit here in the lecture to understand the workings of our network. But by this point, I hope we are all comfortable uh, performing one forward pass through a network. So given two inputs, how do we compute the output? Of course, in practice, most machine learning libraries and packages will allow you to write one-line code that lets you do this. But it's useful to understand the inner workings of this so that we can debug and understand what is going on behind the scenes if we encounter some difficulties or if you want to do something beyond a standard neural network. So now that we know how to compute the output by doing one forward propagation, we need to now understand how the neural network learns this mapping between the Young's modulus and the inputs. At this point, the neural network knows nothing about the physics of the problem, and it will never know anything about the physics of the problem in general. So how does it learn this correlation directly from the data? Well, it does this with a process called backpropagation. So we did a forward pass to predict the value of the Young's modulus, and now we will do backpropagation to train our neural network to learn the mapping. So let's look at how this training is done. The parameters of our neural network are the weights, W1 to W6, and the biases, shown here in red and blue. These weights and biases go into activation functions, which give us values for A1 and A2, which are again passed on to get the prediction for the Young's modulus. So we essentially have 9 parameters in this model. So how do we learn this? To do this, we need to first define what is a good prediction and what is a bad prediction, because that is the only way we can train our network to move away from bad predictions and give us predictions that agree with our data. To do this, we need to define quantitatively an error metric, commonly called a loss function or an objective function. One example of which you might have come across before is mean squared error, where you take the model prediction, compare it with the ground truth data, and square it, and take an average over all the samples in your data set to come up with the average squared error on an example in your data set. Another example of this could be mean absolute error and some other variants of it, but the point of this objective function or loss function is to quantitatively define good predictions and bad predictions for a model. And having defined this error metric, we can now use backpropagation to come up with the ideal values for the weights and biases that will give us a good prediction, which by our error metric means a low mean squared error or a low mean absolute error. And the way to do this is using a weight update rule. This is a simple version of gradient descent if you're familiar with optimization algorithms. If not, it is just a scheme to update the value of a weight from whatever its initial value was to a new value that will give us a lower mean squared error, for instance. So W1 is going to be W1 minus some constant alpha times a gradient term. Now this gradient is the gradient of the objective function with respect to the weights and the biases, and this is what we compute using the technique of backpropagation and using the auto differentiation capabilities that most neural network packages have built into them. So the essential point here is that when we are training these neural networks, we start with a random set of weights and biases because we have no other better guess of the correlation between the Young's modulus and the melting temperature and resistivity. And starting from these random weights and biases, we are most likely to make a high error because the random weights and biases do not capture the correlation. But using these weight update rules and the backpropagation method, we can systematically drive the weight values and the bias values to be the optimal values for which we can make good predictions. Now, there's one last thing that we need to know before we go ahead and train our own neural networks in the hands-on sessions, which is pre-processing the inputs for our network. In the schematics that I've been showing, we have two inputs, melting point and resistivity. In general, there could be many inputs, as you'll see in the hands-on tutorials. Now, if we take a closer look at these input values, the raw values from our data, we notice that they are of completely different scales. The melting point is on the order of a few thousand Kelvin. The electrical resistivity is on the order of 10 to the power minus 8 units. So it could be that they're measured in completely different units, but they are of completely different scales. And knowing that a neural network is going to linearly combine these inputs with weights and apply activation functions to them, we could intuitively imagine that combining weights with these inputs would mean that more often than not, the neural network will completely ignore the resistivity just because the values for the resistivity are so low. So how do we tell the neural network not to ignore something like the resistivity here just because of the units that it was measured in, or just because the quantity happened to be on a different scale compared to the other inputs? What we typically do is called normalization. So we normalize our inputs so that these differences in the scale of the properties are removed. And there are two ways to do this. The first is standard score normalization, where we take the input, let's say the melting point, and subtract the mean of the data and divide by the standard deviation of our data. And if our data is normally distributed, this would typically mean that the scaled value of our input, Si, would typically be in the range of -3 to 3. Another scheme to do the same normalization is min-max normalization, where we compute a scaled version of our input, say the melting point or the resistivity, and convert these range of values that we have in our data set to be all lying between a predetermined min and max value. So you could say that the melting point, I'm now going to scale the melting point using min-max normalization such that all the melting point values are now between 0 and 1. And this means that applying this scheme to each column of our data set means that we have now reduced all the inputs to be between -3 to 3 or 0 to 1, let's say, meaning that we have removed this problem of the data being in different scales and different units. And now, having understood this pre-processing step, we are finally ready to train our neural networks. And to see the details of that and the code involved, I would encourage you to look at the hands-on tutorials. What I'm showing you here is the end result of such a training process. It is maybe 5 to 10 lines of code at max to create and train a neural network using Keras or your favorite machine learning package. And what you get is something so powerful and so interesting. So our neural network model to predict the Young's modulus given all this atomic information is extremely good. It's shown here in this parity plot. On the y-axis is the predicted value from our neural network, and on the x-axis is the ground truth data. And we see that there's excellent agreement. It's significantly better than our linear model. And this means that the neural network is able to capture the correlation between the Young's modulus and all this atomic information. So this is quite exciting, and this is indeed how you'd create and train neural networks for a regression task. The regression task here being to predict Young's modulus. In the second half of this lecture, I wanted to talk about creating neural networks for classification tasks, because this is again a common scenario that you might encounter when you are using neural networks in your application of interest. So let's understand this a little bit better. In a regression task, we saw how to predict Young's modulus given the input's melting temperature and resistivity. The key characteristic of a regression task is that the output is a continuous value. So the Young's modulus could be 50 GPa, it could be 51 GPa, it could be any value in between. What is fundamentally different in a classification task is that the neural network now predicts a discrete category. So if we think of predicting a crystal structure, for example, a crystal structure could be either FCC, BCC, face-centered cubic, body-centered cubic, or HCP, hexagonal closed pack, or a set of other crystal structures. It cannot take on any continuous value. there are only so many crystal structures. So how do we account for this distinction? And how do we train a neural network to categorize our inputs into one of many bins? And that is what we will look at in the second half of this lecture. The example, as I just mentioned before, is to predict the crystal structure of our material given the same set of atomic data that we used to predict the Young's modulus, so lattice constants, atomic mass, atomic radii, resistivities, etc. Can we predict the crystal structure of single elements given this information? So the first thing that we need to think about is translating our string representation of a crystal structure like FCC into a numerical output. And the way to do this for classification tasks is to use something called one-hot encoding. It's called one-hot encoding because the encoding scheme converts strings to a list of numbers where only one value is 1 and all the others are 0. For instance, the string FCC, the crystal structure FCC, could be converted to a one-hot encoded value of 1, 0, 0. The BCC crystal structure is going to be 0, 1, 0, and the HCP is 0, 0, 1. So having understood this encoding scheme, how do we now design a network that will give us those three outputs? So in the regression task, our neural network had one output, which was the Young's modulus, and we had one hidden layer and we had weights and biases that connected the inputs to the outputs. Well, a lot of the core concepts remain the same. We will still have weights, we'll still have biases, but to understand this a little bit better, I'm showing a schematic here of a network that has three inputs: melting temperature, resistivity, and atomic mass, and that gives us three outputs, O1, O2, and O3. And we have one hidden layer just as before, but now it has three neurons. The only difference here is that the output layer is going to use a very special activation function called the softmax activation function. So to understand this softmax activation, let's look at the output O1. And let's assume that the inputs to this neuron O1, which are obtained by a linear combination of weights and biases using the values in the hidden layer, are encoded in a variable Z1. So if the input to the neuron O1 is Z1, the softmax activation is going to apply to Z1 in such a way that the output Y1 hat is now going to be e to the power Z1 divided by e to the power Z1 plus e to the power Z2 plus e to the power Z3, where Z2 and Z3 are the corresponding inputs to the neurons O2 and O3. So if we work through an example, as you'll do in the hands-on tutorials and in the homework assignments, you will see that typical outputs of this softmax activation could be something like this. O1 is going to be 0.65, O2 is going to be 0.25 maybe, and O3 is 0.1. This is an example output. And the reason to introduce this example output is to understand the nature of the softmax activation. One thing that you will notice is that the sum of these three numbers, O1, O2, and O3, is 1, and that all these numbers are positive. And that is indeed a characteristic of the softmax activation function. The softmax activation is always going to produce outputs that are greater than 0 and less than 1, such that the sum of all the outputs, in this case we have 3, will always be equal to 1. And this means that we can interpret the outputs as probabilities, which is very useful because the objective function that we will define will use these probabilities. So just to complete the example here, let's say we have a neural network that has inputs as melting temperature, resistivity, and atomic mass. The outputs O1, O2, O3 could turn out to be numbers like this I'm showing here. And to convert this into a crystal structure prediction, we will take the maximum value that we see out of these three numbers, which is 0.65, and say that O1 has the maximum value, which means the crystal structure predicted is FCC. If O2 had the maximum value out of the three, we would predict our crystal structure to be BCC. So the network prediction is the maximum of the three outputs. So how do we train this neural network, and why are we using the softmax activation? Well, the softmax activation allows us to interpret the outputs as probabilities, just as I said before, which means that we can now define a loss function or an objective function called the categorical cross-entropy loss function, which in some sense measures the difference in the probability distribution that is predicted by a neural network and the probability distribution that is present in the ground truth dataset. And the details of this are a story for another time, but the use of the softmax activation is so that we can use something like the categorical cross entropy to define how poorly or how well is our network performing. And just as always, we will start with random weights and biases, which may or may not give us good predictions. But to update the weights systematically based on the loss function, we will again use backpropagation and a weight update rule, just like we did for the regression task. And one other metric that we often use in classifications, in addition to the loss function, is accuracy, because the categorical cross entropy is a loss function that may or may not be the most intuitive, unlike the mean square error. One metric for model success is often accuracy. So how accurate are your predictions? And just to give an example, if the ground truth data for, say, something like copper is FCC, our network should predict FCC, and if it does so, the network is correct. If not, the network is incorrect. And we can measure this across our data set and define the accuracy to be the number of times we make correct predictions divided by the total number of predictions we make. So just to give you an example, an accuracy of 80% means that we predict the correct crystal structure about 80% of the time. So having understood how to train these neural networks, I will again encourage you to go to the hands-on tutorials to look at the coding aspects of this and how to define networks that are not as simple as this schematic, but to still achieve the same output. But I'm showing you here the results of training such a classification network. The first thing that we can do is just list our predictions for the materials in the training set, comparing them to the true crystal structures. So for atomic number 27, the true crystal structure is HCP, and we predict HCP. So that's pretty good. And we can also visualize the raw outputs of our networks, which are, remember, a set of 3 numbers. And we use the maximum of those 3 numbers to come up with the predicted crystal structure. So we see that for something like nickel, our network predicts the FCC crystal structure with a probability of about 70%, which means that the network thinks it's likely that nickel is an FCC crystal, which agrees with our ground truth data and agrees with our prior knowledge. And we can do the same thing for BCC and HCP materials, and we see that we get it right most of the times. There are a few outliers here, but our neural network is pretty good at predicting the crystal structure of single elements given atomic information. The last thing that we need to understand before we go off and create our own neural networks for a wide variety of applications is to understand how we can determine if our neural network or if our model in general has learned all that it could. If you imagine this cloud of data points here, which will help us understand this example before we apply it to neural networks, we know that this cloud of points follows something more than a linear trend. It looks a lot like a quadratic data set. So fitting a straight line to this data is underfitting our data because there is a bigger trend in this data that we are not capturing. On the other hand, a curve like this that passes through all the data points and is extremely high order, so this could be like a 10th order polynomial, is overfitting our data because all it has done is memorized the training data and has ignored the underlying trend, which is the quadratic curve in this case. So how do we make this balance between creating a model that does not capture the trend in the training data to creating a model that completely memorizes the data and again ignores the trend? Well, what we need to do is define a fine balance between this overfitting and underfitting regimes and come up with a model that is optimal. And we can control the model nature by adding more layers to our network or removing some layers to our network or removing or adding neurons to our network. And the process to do this is to often employ something called a validation set. So far I've talked about data and using that data to train our network and obtain predictions. To dive a little more deeply into that, what we normally do is divide our data set into a training and a validation set. So A training set is the model that you use to train the data. So that is the data set that will be used to update the weights and the biases of that network given the objective function that you specified. The validation set is what is used to check the, the predictions of a model on data that it has not seen in the training process. And this is useful because the validation set is a useful indicator of how well the model would perform on something it hasn't seen before. So how well does the model generalize? So you'd imagine that for an underfit model where we don't capture the trend in the data at all, we're going to make pretty high errors on the training set because there's much more to be learned here. And there's also going to be a high error on the validation set because if we have not captured the trend in the training data, we are unlikely to capture the trend in the validation data, so our error is going to be high. So a high training error and a high validation error is an underfit model. On the other hand, if you have an extremely low training error, but you have a high validation error, this means that the model has learned everything that it could from the training set, but it has learned it in such a way that for some unseen data that is in the validation set, the model performs extremely poorly. So the validation error is high. This means that our model has probably not learned a lot from the data. It has just memorized the training data, and that is why we get a high validation error, which means that our model is overfitting. So the correct balance between the two is for us to have a model that has a relatively low training error, also a relatively low validation error. And that would be a model that is neither overfitting nor underfitting. And there are various methods to do this. For neural networks, we can use something called early stopping, which you will see in the hands-on tutorials. But there are various other methods that are used for other models, such as cross-validation and so on. One thing to note in this table is this column called testing error. So the testing data set is the models that you will finally use to make predictions given the iterations between the training and the validation sets to achieve an ideal model. And with that, we are pretty much done. We now know how a neural network looks like and how it learns complex mappings between inputs and outputs based on the weights and the biases. We saw how to train neural networks for regression and classification tasks and defining different objective functions that are relevant to those tasks. And we saw a little bit about how using a validation set can help us understand how to choose the number of layers or the number of neurons in each layer such that we avoid underfitting or overfitting. The next steps for you, if you've made it this far, is to try the hands-on tutorials, which will introduce you to the programming aspects of this lecture and help you understand these concepts in more details. And try out the homework assignment, which will reinforce some of these concepts and help you feel comfortable with the material that is covered here and in the hands-on programming, and hopefully let you walk away from this module with the confidence to create and train neural networks for your application of task. See you next time.